Right now, as you sit there listening to this, your body is burning through energy. The food you ate today is being converted into heat, into motion, into the electrical signals firing between your neurons. And when that energy leaves your body as warmth radiating off your skin, it doesn't vanish. It enters the air around you, gets absorbed by the walls, eventually radiates into space. That energy still exists. Every single bit of it. In fact, here's what's going to bend your mind tonight. The energy warming your coffee this morning has existed since the beginning of the universe. It was never created. And no matter what happens, it can never be destroyed. And the reason why is connected to something even deeper than physics. It's connected to the nature of time itself. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, even if you've never thought about it in these terms. You understand energy. You feel it every day. When you wake up in the morning after a good night's sleep, you feel energized. After running up a flight of stairs, you feel drained. When you eat a meal, you feel replenished. These aren't just metaphors. Your body is literally processing energy, converting it from one form to another, using it to keep you alive. Energy is one of those words that everyone uses, but almost nobody can precisely define. Ask 10 people what energy is, and you'll get 10 different answers. Power, force, strength, fuel, electricity, heat, motion. All of these are related to energy, but none of them are energy itself. Physicists have struggled with this too. Richard Feynman, one of the greatest physicists of the 20th century, once said that we have no knowledge of what energy is. We know how to calculate it. We know how to measure it. We know how it behaves. But what it actually is, at its deepest level, remains mysterious. What we do know is that energy is a quantity, a number we can assign to any physical system that tells us something fundamental about that system's ability to cause change. Energy is the capacity to do work. That's the textbook definition, and it's useful as far as it goes. But it barely scratches the surface of what energy really means and why it matters. Let's go back to the beginning, back to a time when nobody understood energy at all. For most of human history, people had no concept of energy as a unified thing. They experienced heat, and they experienced motion, and they experienced light, but they didn't realize these were all manifestations of the same underlying quantity. Heat was one thing, motion was another, light was something else entirely. They seemed completely different, and there was no reason to think they were connected. The ancient Greeks had some ideas about motion that influenced thinking for nearly 2,000 years. Aristotle believed that objects naturally came to rest. If you pushed a car, it moved. When you stopped pushing, it stopped moving. This seemed obviously true. Everything around us slows down and stops unless something keeps pushing it. A ball rolling across the ground gradually comes to a halt. A spinning top eventually wobbles and falls. A pendulum swings back and forth but eventually hangs still. Where does the motion go? In Aristotle's framework, the motion simply ceased. It didn't go anywhere, it just stopped existing. The object returned to its natural state of rest. This view dominated Western thinking for almost 2 millennia. But there were always puzzles. If you rub your hands together vigorously, they get warm. Where does that warmth come from? If you bang a hammer against a piece of metal over and over, the metal gets hot. Hot enough to burn you. What's happening there? Heat seemed to appear from nothing whenever things rubbed or crashed together, and conversely, a hot object left alone gradually cooled down. The heat seemed to disappear into nothing. In the 17th century, the great scientific revolution began to change how people thought about the physical world. Galileo Galilei showed that objects in motion tend to stay in motion unless something slows them down. A ball rolling on a flat, frictionless surface would roll forever. This was a radical idea. It meant that motion wasn't something that needed a constant cause. Motion was natural. It was stopping that required an explanation. Isaac Newton formalized this insight in his Laws of Motion, published in 1687. His first law states that an object in motion stays in motion at the same speed and in the same direction unless acted upon by an external force. His second law quantified how forces change motion, and his third law said that every action has an equal and opposite reaction. Newton's framework was revolutionary, but it didn't include a concept of energy as we understand it today. Newton talked about forces and motion, not about energy. The word energy in its modern scientific sense wouldn't be coined until the 19th century. However, something important was brewing. In 1686, the year before Newton published his masterpiece, a German mathematician and philosopher named Gottfried Wilhelm Leibniz proposed a quantity he called vis viva, which is Latin for living force. Leibniz argued that there was a quantity associated with the moving objects that was conserved, that didn't change even when objects collided and bounced off each other. He defined vis viva as the mass of an object multiplied by the square of its velocity. This is remarkably close to our modern concept of kinetic energy, which is 1/2 times mass times velocity squared. Leibniz was onto something profound. He was noticing that when objects interact, something is preserved. Not the speed of individual objects, because that changes. Not the force, because that comes and goes. But something deeper. Some quantity that doesn't increase or decrease, that merely transfers from one object to another. But Leibniz's vis viva had a problem. It wasn't always conserved. When a ball bounced on the ground, it bounced a little lower each time. The vis viva decreased with every bounce until the ball sat motionless on the ground. Where did the vis viva go? Nobody could answer that question, and it haunted natural philosophers for over a century. The mystery deepened when people started paying more attention to heat. In the 18th century, the dominant theory of heat was the caloric theory. This theory, championed by the great French chemist Antoine Lavoisier, proposed that heat was an invisible, weightless fluid called caloric. Hot objects contain more caloric than cold objects. When a hot object touched a cold one, caloric flowed from hot to cold until they reached the same temperature. This theory worked remarkably well for many situations. It explained heat conduction. It explained why mixing hot and cold water gives you warm water. It explained why metals felt cold to the touch, because metals conduct caloric away from your skin faster than wood does. The caloric theory was elegant and seemed to account for everything people observed about heat. But there was a crack in the foundation. In 1798, an American-born scientist named Benjamin Thompson, who held the title Count Rumford, was overseeing the boring of cannon barrels at the military arsenal in Munich. Boring a cannon barrel means drilling a hole through a solid cylinder of metal, and the process generates enormous amounts of heat. The metal shavings got so hot they could boil water. This wasn't surprising by itself. The caloric theory could explain it by saying that the solid metal contained caloric, and when you ground it into small pieces, the caloric was released. But Rumford noticed something the caloric theory couldn't explain. The heat seemed inexhaustible. As long as the boring tool kept grinding, heat kept coming. He could produce heat endlessly just by continuing to apply friction. If heat were a fluid contained within the metal, eventually the metal should run out of caloric and stop producing heat. But it never did. Rumford wrote that anything which any insulated body can continue to furnish without limitation cannot possibly be a material substance. He concluded that heat must be a form of motion, not a substance. The friction of the boring tool was converting the mechanical motion of the drill into the motion of the metal's particles, which we perceive as heat. Rumford was right, but his argument didn't immediately overthrow the caloric theory. The theory was too well established, too useful in too many situations. Most scientists continued to use caloric theory for decades after Rumford's experiment. The idea that heat and motion were somehow the same kind of thing seemed bizarre. How could the movement of a cannonball through the air be the same kind of thing as the warmth of a fire? Meanwhile, the concept of energy was slowly crystallizing from multiple directions. In the early 1800s, the connections between different physical phenomena started to become apparent. In 1800, Alessandro Volta invented the electric battery, showing that chemical reactions could produce electricity. In 1820, Hans Christian Ørsted discovered that electric currents produce magnetic fields. In 1831, Michael Faraday showed that changing magnetic fields produce electric currents. Electricity could produce magnetism, and magnetism could produce electricity. These weren't separate things. They were deeply connected. And then there was light. In the 1860s, James Clerk Maxwell would show that light is an electromagnetic wave, unifying optics with electricity and magnetism. But even before Maxwell's breakthrough, it was becoming clear that the physical world was far more interconnected than anyone had realized. Heat, motion, electricity, magnetism, light, chemical reactions, all of these seem to be different aspects of something. Different currencies that could be exchanged for one another. This brings us to one of the most important but least celebrated insights in all of science. The realization that all these different phenomena shared something in common. That there was a single quantity, what we now call energy, that was being converted from one form to another in all these processes. And this quantity, this energy was never being created or destroyed. It was only being transformed. Let me walk you through the different forms of energy, because understanding these forms is crucial to understanding why energy never disappears. It doesn't disappear because it changes its clothing. It puts on a different disguise, but it's still there. Kinetic energy is the energy of motion. Anything that's moving has kinetic energy. A baseball flying through the air, a car driving down the highway, a molecule vibrating in a gas, an electron orbiting an atomic nucleus. The faster something moves, the more kinetic energy it has. And the more massive it is, the more kinetic energy it has at the same speed. A truck moving at 60 miles per hour has far more kinetic energy than a tennis ball moving at the same speed. Potential energy is stored energy. Energy that exists because of an object's position or configuration. A book sitting on a shelf has gravitational potential energy. If you push it off the shelf, gravity pulls it down, and that potential energy converts into kinetic energy as the book accelerates toward the floor. A compressed spring has elastic potential energy. Release it, and the spring snaps back, converting that stored energy into motion. A boulder balanced on the edge of a cliff has enormous potential energy. One small push and gravity converts all that stored energy into devastating kinetic energy as the boulder tumbles down the mountainside. Thermal energy is the energy of random molecular motion. Every object in the universe, no matter how still it appears, is actually seething with internal motion. The atoms and molecules that make up everything are constantly vibrating, rotating, and bouncing off each other. The faster they move, the hotter the object feels. Temperature is really just a measure of how vigorously the particles in a substance are moving. When you touch a hot stove, the rapidly vibrating molecules in the metal transfer their kinetic energy to the molecules in your skin, which your nerves register as pain. Chemical energy is the energy stored in the bonds between atoms. When you eat food, your body breaks the chemical bonds in the food molecules and rearranges the atoms into new molecules. This process releases energy that your cells use to function. When you burn wood in a fireplace, the chemical bonds in the wood molecules and the oxygen molecules are broken, and new bonds form in carbon dioxide and water. The energy released by this rearrangement of bonds manifests as heat and light. The energy was there all along, stored in the arrangement of atoms. Electrical energy is the energy associated with the flow of electric charges. When electrons move through a wire, they carry energy from one place to another. This is what happens when you plug in a lamp. Electrons flow through the wire, carrying energy from the power plant to the light bulb, where it's converted into light and heat. Radiant energy is the energy carried by electromagnetic waves. Light, radio waves, microwaves, X-rays, gamma rays, all of these are forms of electromagnetic radiation, and all of them carry energy. The sunlight that warms your face carries radiant energy that traveled 93 million miles from the sun to reach you. That energy started as nuclear energy in the sun's core, was converted to thermal energy, then to radiant energy, and now it's warming your skin, being converted back into thermal energy. Nuclear energy is the energy stored in the nuclei of atoms. This is by far the most concentrated form of energy. The nucleus of a single uranium atom contains millions of times more energy than a single chemical bond. When a uranium nucleus splits in a nuclear reactor, a tiny fraction of its mass is converted directly into energy, and that tiny fraction is enough to generate enormous amounts of heat. This is also where the sun gets its power. Deep in the sun's core, hydrogen nuclei are fused together to form helium, and a small fraction of their mass is converted into the energy that lights up the solar system. Now here's the key insight, the thing that ties all of this together. All of these forms of energy are interconvertible. You can convert any form of energy into any other form of energy. Kinetic energy can become thermal energy through friction. Chemical energy can become electrical energy in a battery. Electrical energy can become radiant energy in a light bulb. Nuclear energy can become thermal energy in a reactor. Radiant energy can become chemical energy in a plant through photosynthesis. And on and on and on. Every physical process you've ever witnessed is, at its heart, a conversion of energy from one form to another. When you drop a ball, gravitational potential energy converts to kinetic energy as it falls. When it hits the ground, kinetic energy converts to thermal energy and sound energy. The ball bounces back up, converting some kinetic energy back into potential energy. But it doesn't bounce quite as high because some energy was converted to heat and sound during the impact. Each bounce is a little lower, eventually the ball sits still on the ground. Has the energy disappeared? Absolutely not. Every single joule of the original potential energy still exists. It's been converted into thermal energy, warming the ball and the ground by an imperceptibly tiny amount. It's been converted into sound energy, which travelled outward and was eventually absorbed by the walls and furniture, warming them by an even more imperceptibly tiny amount. The energy is all still there. It's just been spread out and converted into a form that's harder to detect and harder to use. This is what Leibniz was missing with his vis viva. He was tracking the energy of motion, kinetic energy, but he didn't realize it was being converted into heat. When a ball lost its bounce, the vis viva wasn't disappearing. It was becoming thermal energy, the random jiggling of trillions of atoms, invisible and seemingly gone, but absolutely still present. This is also what Count Rumford was observing with his cannon boring. The mechanical energy of the drill wasn't disappearing into the metal. It was being converted into thermal energy through friction. The supply of heat was inexhaustible because the drill kept supplying mechanical energy, and that energy kept being converted into heat. As long as energy was going in through the motion of the drill, energy was coming out as heat. Nothing was being created from nothing. Nothing was disappearing into nothing. Energy was being transformed. Think about your own body for a moment. You eat food. The chemical energy in that food is broken down in your digestive system. Some of that energy is used to power your muscles, allowing you to move. But muscles aren't perfectly efficient. Most of the chemical energy is converted into thermal energy. This is why you're warm. Your body temperature of around 98.6 degrees Fahrenheit is maintained by the continuous conversion of chemical energy into thermal energy. If you stopped eating, you'd eventually cool down and die. Not because energy disappeared, but because you'd run out of chemical energy to convert. When you exercise, you convert more chemical energy into kinetic energy and thermal energy. This is why you get hot when you run. Your muscles are doing mechanical work, but they're also generating a lot of heat. That heat has to go somewhere, so your body sweats. The water evaporating from your skin carries thermal energy away. That energy heats the surrounding air. The heated air rises and mixes with cooler air. The energy spreads out, becoming harder to track, harder to measure, but it never vanishes. Consider a car driving down a highway. The engine burns gasoline, converting chemical energy into thermal energy and then into the kinetic energy of pistons, which turns the wheels. But the car also pushes against air resistance, converting kinetic energy into thermal energy that heats the air behind the car. The tires press against the road, and friction converts some kinetic energy into thermal energy that heats the tires and the road surface. The brakes, when applied, convert kinetic energy into thermal energy through friction between brake pads and rotors. When the car finally stops, all the chemical energy that was in the gasoline has been converted into thermal energy, warming the engine, the air, the road, the brakes, and everything else the car interacted with. And some became sound energy. The roar of the engine, the hiss of tires on pavement, which spread out through the air and was absorbed by surroundings, becoming more thermal energy. Every joule in the gasoline is accounted for. Nothing was lost. A waterfall provides another beautiful example. Water at the top of the falls has gravitational potential energy. As it plummets, that potential energy converts to kinetic energy. The water accelerates, moving faster and faster. When it crashes into the pool below, the kinetic energy is converted into thermal energy, sound energy, and the kinetic energy of the splashing water. The pool at the bottom of a waterfall is very, very slightly warmer than the water at the top. The great physicist James Joule, whom we'll talk about soon, actually tried to measure this temperature difference on his honeymoon in 1847. He and his wife visited a waterfall in France, and Joule attempted to measure the temperature of the water at the top and bottom. The difference was far too small for his instruments to detect, but in principle, it's there. Every bit of potential energy the water lost by falling was converted into thermal energy warming the pool. By the early 19th century, the pieces were falling into place: heat, motion, electricity, magnetism, light, chemistry. These were all connected. They were all forms of something that could change its appearance, but never its total amount. But proving this, quantifying it, turning an intuition into a law of nature, that will require careful experiments and brilliant minds. And the story of how that happened is one of the greatest detective stories in the history of science. The stage was set. Count Rumford had shown that heat could be produced endlessly from motion. Faraday and Ørsted had shown the deep connections between electricity and magnetism. The idea that different physical phenomena were manifestations of a single conserved quantity was in the air. But nobody had yet nailed it down precisely. Nobody had measured exactly how much heat you get from a given amount of motion. Nobody had proved that the total always balances perfectly. That breakthrough was about to come, and it would come from some of the most unlikely places. But before we get there, I want you to appreciate how radical this idea was. For thousands of years, humans had watched motion die, watched fires burn out, watched hot things cool down. The natural conclusion was that something was being lost, consumed, destroyed. The wood burns and it's gone. The ball stops bouncing and the motion is gone. The hot tea cools and the heat is gone. Everything in our everyday experience seems to tell us that energy gets used up, that it disappears. The claim that energy never disappears, that it merely changes form, that every joule of energy that existed at the Big Bang still exists today and will exist forever. This is one of the most counterintuitive claims in all of science. It contradicts what our senses tell us every day. And yet, it turns out to be one of the most thoroughly tested and most reliably confirmed principles in the history of physics. No experiment has ever found a violation. Not one. Not ever. In more than 170 years of searching across every branch of physics, from thermodynamics to quantum mechanics to general relativity, the conservation of energy has held firm. It's been tested in particle accelerators, in nuclear reactors, in chemical labs, in astronomical observations of stars and galaxies billions of light years away. It always balances. The total energy in a closed system, a system that doesn't exchange energy with its surroundings, never changes. It can transform, it can redistribute, it can concentrate in one place or spread across the cosmos. But the total is always the same. Think about that. In a universe that's 13.8 billion years old, a universe containing 2 trillion galaxies and 200 billion trillion stars, the total amount of energy has never changed, not by a single joule. Every nuclear reaction in every star, every supernova explosion, every black hole swallowing matter, every photon crossing the void between galaxies, all of it transforms energy, moves energy, converts energy from one form to another, but none of it creates energy, and none of it destroys it. This is the law of conservation of energy. And how we discovered it, why it's true, and what it means for the fate of the universe, that's what the rest of this story is about. Consider a lightning bolt for a moment. A single bolt of lightning releases about 1 billion joules of energy in a fraction of a second. That energy existed as electrical potential energy in the charged clouds. When the bolt strikes, it converts into light, heat, and sound. The thunder you hear is sound energy spreading outward. The flash is electromagnetic radiation. The air along the path of the bolt is heated to around 30,000 degrees, about 5 times hotter than the surface of the sun. This super hot air expands explosively, creating the shock wave you hear as thunder. And after the lightning strike, where did all the energy go? It heated the air along the bolt's path. The heated air rose and mixed with surrounding air, spreading the thermal energy across a larger and larger volume. The sound waves traveled outward, gradually weakening as they spread, until they were absorbed by the ground, by buildings, by the atmosphere. The light traveled outward at the speed of light, illuminating the landscape briefly before being absorbed by clouds, the ground, and everything else it hit. Every joule that was in that lightning bolt is still out there, spread thinly across the environment, warming the world by an unmeasurably tiny amount. The energy of the lightning didn't vanish when the flash ended. It dispersed. Or think about a candle. A candle burns and eventually there's nothing left but a small puddle of wax and a charred wick. Where did the candle go? The chemical energy stored in the wax molecules was released through combustion. The wax reacted with oxygen in the air, forming carbon dioxide and water vapor. The energy that held those wax molecules together was released as heat and light. The hot gases rose upward in the flame. The light spread outward in all directions. The carbon dioxide and water vapor dispersed into the room and eventually into the atmosphere. The candle is gone, but its energy remains. Every joule of chemical energy that was stored in the wax has been converted into thermal energy and radiant energy, now spread throughout the room and beyond. If you could somehow track every molecule of carbon dioxide and water vapor that came from that candle, every photon of light it emitted, every convection current, its heat generated, you'd find that the total energy of all those things equals exactly the chemical energy that was originally stored in the wax. Nothing more, nothing less. This is what we're going to explore tonight. How we discovered this extraordinary law, what makes it true at the deepest level, and what it tells us about the ultimate fate of the universe and everything in it. The story of how we prove that energy is conserved begins with a German physician named Julius Robert von Meyer. In 1840, Meyer was working as a ship's doctor on a voyage to the Dutch East Indies, modern-day Indonesia. During the journey, he noticed something peculiar while treating sailors. When he drew blood from sailors in the tropics, their venous blood was unusually red, much brighter than the dark venous blood he was accustomed to seeing in Europe. This might seem like a trivial observation, but Meyer was an unusually deep thinker. He reasoned that the bright color meant the blood contained more oxygen than usual. In cooler climates, the body needs to burn more food to maintain body temperature, using up more oxygen in the process. In the tropics, where the air was warm, the body didn't need to generate as much heat, so less oxygen was consumed, and the venous blood retained more of its red color. This led Meyer to a profound insight. The human body generates heat by burning food. The chemical energy in food is being converted into the thermal energy that keeps the body warm. If the body also does mechanical work, like lifting objects or moving around, that energy also comes from food. The total energy output, heat plus mechanical work, must equal the chemical energy input from food. Nothing is created from nothing. Nothing vanishes into nothing. Energy is merely being converted from one form, chemical, into other forms, thermal and mechanical. Mayer published his ideas in 1842 in a paper that proposed a general principle. All forms of energy are convertible into one another, and the total amount of energy is always conserved. He even attempted to calculate the conversion factor between mechanical work and heat, what would later be called the mechanical equivalent of heat. His result was roughly in the right ballpark, though not terribly precise. He calculated that the amount of mechanical work needed to raise the temperature of 1 kilogram of water by 1 degree Celsius was about 365 kilogram meters of work. But Mayer was a physician, not a physicist. His paper was published in a chemistry journal, and his arguments were more philosophical than mathematical. The physics establishment largely ignored him. His ideas were ahead of their time, and he lacked the experimental evidence and mathematical rigor needed to convince skeptics. Mayer would later suffer a mental breakdown partly due to the frustration of not receiving recognition for his ideas. The experimental proof came from an unexpected source. James Prescott Joule was the son of a wealthy brewer in Manchester, England. He wasn't a professional scientist. He was an amateur, a gentleman scientist who conducted experiments in a laboratory next to his family's brewery. But Joule had something many professional scientists lacked. He had an extraordinary talent for precise measurement, a near obsessive dedication to accuracy, and access to good thermometers, which was crucial because measuring small temperature changes was the key to his experiments. Joule started by studying the relationship between electricity and heat. In the early 1840s, he showed that when electric current flows through a wire, the wire heats up, and the amount of heat produced is proportional to the square of the current times the resistance of the wire. This relationship, now called Joule's first law, showed a precise mathematical connection between electrical energy and thermal energy. A specific amount of electrical energy always produced a specific amount of heat, no more, no less. This encouraged Joule to look for similar relationships between other forms of energy. In 1843, he presented a paper to the British Association for the Advancement of Science, in which he described experiments showing that mechanical work could be converted into heat at a fixed rate. He had connected a small electric generator to a falling weight. As the weight fell, it turned the generator, which produced electric current, which flowed through a wire which heated water. Joule carefully measured the weight's height, the distance it fell, and the temperature change in the water. He found a consistent relationship. A specific amount of mechanical work always produced a specific amount of heat. But his most famous experiment was even more direct. Joule built an apparatus that's now known as Joule's apparatus, or the paddle wheel experiment. It consisted of a large insulated container of water with a paddle wheel inside. The paddle wheel was connected via a pulley to falling weights. As the weights fell, they turned the paddle wheel, which churned the water. The friction between the paddle and the water heated the water slightly, very slightly. Joule had to measure temperature changes of fractions of a degree. Joule performed this experiment with incredible care and repeated it many, many times. He used sensitive thermometers that could detect changes of 1/200th of a degree Fahrenheit. He carefully insulated his apparatus to prevent heat from leaking in or out. He waited for temperature equilibrium before taking readings. He accounted for the heat capacity of the container itself. He was meticulous to an extraordinary degree. The result was precise and consistent. Every time, the same amount of mechanical work produced the same amount of heat. Joule found that the amount of work needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit was about 772 foot-pounds of work. In modern metric units, this translates to approximately 4.18 joules of mechanical work per calorie of heat. This number is called the mechanical equivalent of heat, and it's one of the most important measurements in the history of science. What made Joule's result so powerful was its universality. It didn't matter how the mechanical work was done, whether through a paddle wheel churning water, through the compression of a gas, through the friction of metal surfaces rubbing together, the conversion factor was always the same. A given amount of mechanical work always produced the same amount of heat. This strongly suggested that mechanical energy and thermal energy were the same thing, just in different forms, and that the conversion between them was governed by an exact mathematical relationship. Joule presented his results at a meeting of the British Association in 1847. The audience was politely skeptical. Temperature differences of fractions of a degree, measured in a brewer's laboratory, it seemed too precise, too good to be true, but one person in the audience was intrigued. A young Scottish physicist named William Thomson, later known as Lord Kelvin, asked pointed questions and recognized the significance of Joule's work. Thomson became one of Joule's most important advocates and collaborators. Meanwhile, in Germany, a brilliant young physician and physicist named Hermann von Helmholtz was independently developing the same ideas from a more mathematical perspective. In 1847, the same year Joule was presenting his paddle wheel results, Helmholtz published a landmark paper titled On the Conservation of Force. In this paper, Helmholtz provided a comprehensive mathematical framework showing that the total energy of a closed system is constant. He demonstrated that energy conservation applied not just to mechanical systems, but to heat, electricity, magnetism, and chemistry as well. Helmholtz's paper was remarkable for its scope and rigor. He showed that if you added up all the kinetic energy and all the potential energy in a closed system, accounting for all forms including heat and chemical energy, the total never changed. He derived this result mathematically from Newton's laws and showed that it applied universally. Any system that obeyed Newton's laws must conserve energy. It wasn't just an empirical observation, it was a mathematical consequence of the fundamental laws of physics. Between Mayer's philosophical insight, Joule's precise experiments, and Helmholtz's mathematical framework, the principle of energy conservation was firmly established by the late 1840s. It became known as the first law of thermodynamics. Energy cannot be created or destroyed. It can only be transformed from one form to another. The total energy of a closed system is constant. The first law of thermodynamics is arguably the most important principle in all of physics. Governs everything. Every engine, every machine, every biological process, every chemical reaction, every physical process in the universe obeys this law. Let me walk you through some examples to show how universal it is. Consider a hydroelectric dam. Water sits in a reservoir at the top of a dam. This water has gravitational potential energy because of its height above the turbines at the bottom. When the water is released, it flows down through pipes, converting potential energy into kinetic energy. The fast-moving water spins turbines, converting kinetic energy into rotational kinetic energy. The turbines are connected to generators, which convert rotational kinetic energy into electrical energy through electromagnetic induction. The electrical energy travels through power lines to your home, where it's converted into light in your lamps, thermal energy in your heaters, kinetic energy in your washing machine, sound energy in your speakers. At every step, energy is transformed from one form to another, and at every step, the total is conserved. The electrical energy produced by the dam exactly equals the gravitational potential energy lost by the water, minus the energy lost to friction and other inefficiencies. And that lost energy isn't really lost. It's been converted to thermal energy, warming the turbines, the pipes, and the water itself. Consider a nuclear power plant. Uranium atoms in the reactor core undergo fission, splitting into smaller atoms. The total mass of the products is very slightly less than the mass of the original uranium atoms. That missing mass has been converted into energy according to Einstein's famous equation, which we'll explore later. This energy appears as kinetic energy of the fission fragments and neutrons, which collide with surrounding atoms, converting their kinetic energy into thermal energy that heats the reactor core. The hot core heats water, turning it into steam. The steam spins a turbine, converting thermal energy into kinetic energy. The turbine drives a generator, converting kinetic energy into electrical energy. Again, at every step, energy is converted from one form to another, and the total is always conserved. Consider photosynthesis, one of the most important chemical processes on Earth. A plant absorbs sunlight, which is radiant energy from the sun. Using that energy, the plant splits water molecules and combines the hydrogen with carbon dioxide from the air to produce glucose, a sugar molecule. The radiant energy from the sun has been converted into chemical energy stored in the glucose molecule's bonds. When you eat that plant, or when an animal eats it and you eat the animal, your body breaks down the glucose, releasing the stored chemical energy and using it to power your muscles, your brain, your organs. The energy that originated as nuclear energy in the sun's core traveled as radiant energy across 93 million miles of space, was captured by a plant and stored as chemical energy, then released in your body as thermal and mechanical energy. The same energy transformed and transferred across millions of miles and billions of years of evolution, never created, never destroyed. Now let me tell you about perpetual motion machines, because they're perhaps the most compelling proof that energy conservation is real. A perpetual motion machine is a hypothetical device that runs forever without any energy input. It either produces energy from nothing, which violates the first law of thermodynamics, or it converts energy with perfect efficiency, which, as we'll see later, violates the second law. Throughout history, thousands of inventors have claimed to have built perpetual motion machines. They've designed elaborate systems of wheels, weights, magnets, fluids, gears, and levers that supposedly generate energy indefinitely. Some of these designs are genuinely clever. They use hidden sources of energy or subtle mechanisms that aren't immediately obvious, but every single one of them, without exception, has been shown to be either a fraud or a mistake. In the 18th century, Johann Bessler, a German inventor, claimed to have built a self-turning wheel that ran for weeks at a time. He demonstrated it publicly and it seemed to work. But skeptics noticed that he always positioned the wheel near a particular wall, and when the device was examined more carefully, evidence of hidden mechanisms was found. Many believe Bessler was operating the wheel through a concealed connection to a hand crank in an adjacent room. The United States Patent and Trademark Office has an official policy of not granting patents for perpetual motion machines. They've been burned too many times. Any patent application claiming to have created a perpetual motion machine is automatically rejected unless the inventor provides a working model. Nobody ever has. The reason perpetual motion machines are impossible is precisely because energy is conserved. You can't get energy out of nothing. Every machine that does work needs an energy source. An engine needs fuel, a solar panel needs sunlight, a windmill needs wind, a battery needs to be charged. You can convert energy from one form to another, but you can't create it. And you always lose some to friction, to heat, to sound. There's always some energy that gets converted into forms you didn't want. No machine is perfectly efficient. This might sound limiting, and in a sense it is. The conservation of energy means there's no free lunch in the universe. You can't get something for nothing. Every joule of useful work you extract from a system must come from somewhere. But it's also profoundly reassuring. It means the universe plays by consistent rules. It means the total energy of the universe is a bookkeeping system that always balances. It means that when you burn food for energy, you're not consuming anything fundamental. You're just rearranging energy, moving it from one form to another. The first law of thermodynamics has been tested in every conceivable way. Nuclear physicists have verified it in particle collisions, at energies far beyond anything found in nature on Earth. Chemists have verified it in millions of chemical reactions. Engineers rely on it every day to design engines, power plants, and electrical systems. Astronomers use it to understand the energy output of stars and the dynamics of galaxies. Biologists use it to understand metabolism and ecosystems. Every branch of science relies on energy conservation, and none has ever found a violation. Let me give you a particularly elegant example. In 1930, the physicist Wolfgang Pauli was studying a type of radioactive decay called beta decay. In beta decay, a neutron in an atomic nucleus transforms into a proton, emitting an electron in the process. The problem was that the electron didn't always come out with the same energy. Sometimes it came out with a lot of kinetic energy, sometimes with very little. And when Pauli added up all the energy he could detect, the total energy after the decay was less than the total energy before. Energy seemed to be disappearing. Now, Pauli could have done what some scientists suggested. He could have abandoned the principle of energy conservation for beta decay. Maybe energy wasn't conserved in nuclear reactions. Maybe there was something special about the weak nuclear force that allowed energy to be created or destroyed. Some prominent physicists, including Niels Bohr, seriously entertained this possibility, but Pauli refused. He had such faith in energy conservation that instead of abandoning the principle, he proposed the existence of an entirely new particle, one that nobody had ever detected, one that was carrying away the missing energy. He called it the neutron, though it was later renamed the neutrino, meaning little neutral one in Italian, to distinguish it from the much larger neutron that had been discovered in the nucleus. Pauli's prediction was bold, perhaps even audacious. He was postulating the existence of an undetected particle purely to save the principle of energy conservation. The neutrino would have to be electrically neutral, have extremely small or zero mass, and interact so weakly with matter that it could pass through the entire Earth without hitting a single atom. Many scientists thought the idea was far-fetched, but Pauli was right. In 1956, 26 years after Pauli's prediction, physicists Clyde Cowan and Frederick Rains detected the neutrino experimentally. The missing energy in beta decay was indeed being carried away by neutrinos. Energy was conserved after all. The universe wasn't cheating. It was just hiding some of the energy in a particle so ghostly that it took a quarter century and revolutionary experimental techniques to detect it. This story illustrates something important about energy conservation. It's not just a law, it's a faith, a principle so deeply embedded in physics that scientists will postulate entirely new particles rather than abandon it. And every time they've done so, they've been vindicated. The universe really does conserve energy, always, without exception. By the middle of the 19th century, the first law of thermodynamics was established. Scientists knew that energy was conserved. They had precise measurements of the mechanical equivalent of heat. They had mathematical frameworks showing how energy conservation followed from the fundamental laws of mechanics. They understood the many forms energy could take and how those forms could be converted into one another. But a deeper question remained. Why? Why is energy conserved? Is it just an empirical observation? Something we've measured to be true but don't understand the reason for? Or is there a deeper explanation? Something that tells us not just that energy is conserved, but why it must be. That deeper explanation would come from one of the most remarkable minds of the 20th century. A mathematician whose contributions were so fundamental that Albert Einstein described her as the most significant creative mathematical genius produced since the higher education of women began. Her name was Emmy Noether, and her theorem, published in 1918, would reveal that the conservation of energy isn't just a law of physics. It's a consequence of the deepest symmetry in the universe. But before we get to Noether, I want to make sure you fully appreciate what the first law means in practice. Because it's not an abstract principle that lives only in textbooks. It's at work in every single thing that happens around you. Right now, as you listen to this, the device you're using to listen to this, whether it's a phone, a laptop, or speakers connected to a computer, it's converting electrical energy into sound energy. That sound energy is traveling through the air as pressure waves, reaching your ears, where it's converted into mechanical energy as your eardrum vibrates, then into electrical energy as the cochlea in your inner ear converts those vibrations into nerve impulses, then into chemical energy as neurotransmitters fire in your brain, creating the experience of hearing. At every step, energy is being transformed, and at every step, the total is conserved. Even thinking requires energy. Your brain, which makes up only about 2% of your body weight, consumes about 20% of your body's total energy. Neurons fire by moving ions across their membranes, which requires chemical energy. The chemical energy comes from glucose in your blood. The glucose came from food you digested. The food grew using energy from the sun. The sun generates energy through nuclear fusion. The hydrogen fuel for that fusion was created in the Big Bang. The energy powering your thoughts right now has a lineage that stretches back 13.8 billion years to the very beginning of the universe. Think about the sound of your own voice. When you speak, Your brain sends electrical signals through nerve fibers to your vocal cords. The muscles in your larynx contract, converting chemical energy into mechanical energy. Your vocal cords vibrate, creating pressure waves in the air. These sound waves carry kinetic energy as the air molecules push against each other in waves spreading outward from your mouth. The sound waves gradually lose intensity as they spread out and as some of the energy is absorbed by walls, furniture, and the air itself, being converted into thermal energy. If you shout in an empty field, the sound waves spread outward in every direction and are eventually absorbed by the ground, the air, the trees, everything they encounter. The thermal energy from your voice warms these surroundings by an immeasurably tiny amount, but the energy is still there. Every word you've ever spoken still exists as thermal energy, dispersed and diluted beyond any possibility of detection, but never destroyed. Consider what happens when you charge your phone. Electrical energy from the outlet flows into the battery, where it's converted into chemical energy as lithium ions move between the battery's electrodes. When you use the phone, that chemical energy is converted back into electrical energy, which powers the processor, the screen, the speakers. The screen emits light, which is radiant energy. The processor generates heat, which is thermal energy. The speakers generate sound, which is mechanical energy in the air. When your phone gets warm during heavy use, that's not a flaw. It's the first law of thermodynamics in action. The electrical energy that powers the processor isn't being used with 100% efficiency. Some fraction is inevitably converted to thermal energy, and that thermal energy has to go somewhere. It warms the phone, and the phone warms your hand, and your hand radiates that warmth into the room. Every star in the sky is a testament to energy conservation. Stars are powered by nuclear fusion. In the core of a star like our Sun, 4 hydrogen nuclei are fused together to form one helium nucleus. The helium nucleus has slightly less mass than the 4 hydrogen nuclei combined. That missing mass has been converted into energy. Specifically, each fusion reaction converts about 0.7% of the hydrogen mass into energy. This sounds like a tiny percentage, but when you multiply by the enormous number of reactions happening every second, the energy output is staggering. The Sun converts about 600 million tons of hydrogen into helium every second, and about 4 million tons of that mass is converted directly into energy. That's 4 million tons of matter transformed into pure energy every single second. And the Sun has been doing this for 4.6 billion years. The energy radiated by the Sun in the form of light and other electromagnetic radiation spreads outward in all directions. A tiny fraction of it hits Earth, and that tiny fraction provides almost all the energy that drives our weather, our oceans, our ecosystems, and ultimately our civilization. Solar panels convert the Sun's radiant energy into electricity. Wind turbines capture the kinetic energy of air currents that were set in motion by the Sun's heating of the atmosphere. Fossil fuels are stored solar energy from ancient photosynthesis, millions of years of sunlight captured by plants and compressed underground. Almost all the energy we use on Earth can be traced back to nuclear fusion in the Sun, and that nuclear energy came from the gravitational potential energy of the hydrogen cloud that collapsed to form the Sun 4.6 billion years ago. It's one unbroken chain of transformation, stretching from your light bulb all the way back to the first moments of existence. The conservation of energy also explains why certain things are impossible, not just impractical, but genuinely fundamentally impossible. You can't build a car that runs on nothing. You can't heat your home without an energy source. You can't power a city from thin air. Every machine, every engine, every process that does useful work must have an energy source. This is why the search for renewable energy is so important. We're not creating energy. We're finding ways to tap into natural energy flows, sunlight, wind, tidal forces, geothermal heat, and convert them into forms we can use. The energy was always there. We're just learning better ways to redirect it. Consider the total energy budget of Earth. The Sun delivers about 174 petawatts of power to Earth. A petawatt is 1 quadrillion watts. About 30% of this is reflected back into space by clouds, ice, and the atmosphere. The remaining 70% is absorbed by the oceans, land, and atmosphere. This absorbed energy drives the water cycle, powers the winds, warms the surface, and enables photosynthesis. Eventually, all of this absorbed energy is radiated back into space as infrared radiation. The energy in equals the energy out, plus or minus a tiny imbalance caused by the greenhouse effect that's currently warming the planet. The greenhouse gases in our atmosphere trap some of the outgoing infrared radiation, preventing it from escaping to space. This doesn't violate energy conservation, it just changes the balance. More energy comes in from the sun than goes out through the atmosphere, so Earth's temperature rises until a new equilibrium is reached. The energy isn't being created or destroyed, it's being redistributed. This is the first law of thermodynamics at work on a planetary scale. It governs the climate of our entire world, the same way it governs the cooling of your coffee and the bouncing of a ball. The same principle operating at every scale, from the subatomic to the cosmic. So by the mid-19th century, the conservation of energy was established as a fundamental law. But the question remained, why? Why is this law true? Is it just an accident, a coincidence that all our measurements happen to show energy being conserved? Or is there a deeper reason? Something that explains not just that energy is conserved, but why it must be. The answer came from Emmy Noether, and it's one of the most beautiful ideas in all of science. Noether was born in 1882 in Erlangen, Germany. Her father, Max Noether, was a mathematics professor, and Emmy showed exceptional mathematical talent from a young age. But the world she lived in didn't make it easy. Women were not allowed to enroll as regular students at German universities when she was young. She had to audit classes, sitting in on lectures without official recognition. Eventually, rules changed enough that she could earn her doctorate in 1907. But even after she became one of the foremost mathematicians in the world, she struggled for recognition. She worked for years without pay at the University of Göttingen, barred from holding a formal position because she was a woman. David Hilbert, one of the most famous mathematicians of the era, reportedly said in frustration, "I do not see that the sex of the candidate is an argument against her admission as a professor. After all, we are a university, not a bathhouse." Despite these obstacles, Noether made contributions to mathematics and physics that are still shaping our understanding of the universe more than a century later. Her most famous result, now called Noether's theorem, was published in 1918. It connects two seemingly unrelated concepts, symmetry and conservation laws, and it explains, at the deepest level we know, why energy is conserved. To understand Noether's theorem, we first need to understand what physicists mean by symmetry. In everyday language, symmetry means that something looks the same from different angles. A circle is symmetric because it looks the same no matter how you rotate it. A square has rotational symmetry of 90 degrees. Your face has approximate bilateral symmetry. The left side roughly mirrors the right. But physicists use symmetry in a broader sense. A physical symmetry means that the laws of physics don't change when you make a certain transformation. There are several types of symmetry that are fundamental to physics. Spatial translation symmetry means the laws of physics are the same everywhere. If you perform an experiment in New York, you will get the same results if you perform the identical experiment in Tokyo, on Mars, or in a galaxy a billion light years away, assuming you set up the same conditions. The laws of physics don't depend on where you are. There's nothing special about any particular location in space. Rotational symmetry means the laws of physics are the same in every direction. If you perform an experiment facing north, you'll get the same results facing east, south, west, up, or down. The laws of physics don't depend on which direction you're facing. There's nothing special about any particular orientation. And then there's time translation symmetry. This is the one that matters for energy conservation. Time translation symmetry means the laws of physics are the same at all times. An experiment performed today will give the same results as the identical experiment performed tomorrow, next year, or a billion years from now. The laws of physics don't change over time. The speed of light was the same a billion years ago as it is today. The force of gravity works the same way now as it did when the dinosaurs roamed the Earth. The equations of quantum mechanics will give the same predictions a trillion years from now as they do today. Now, here's what Noether proved. Every continuous symmetry of the laws of physics corresponds to a conserved quantity. Specifically, if the laws of physics don't change when you shift in a particular way, then there's a quantity that is conserved, meaning it doesn't change over time, associated with that shift. Spatial translation symmetry, the fact that the laws of physics are the same everywhere, gives rise to the conservation of momentum. This is why momentum is conserved. It's because space is the same everywhere. If the laws of physics were different in different locations, momentum would not be conserved. Rotational symmetry, the fact that the laws of physics are the same in every direction, gives rise to the conservation of angular momentum. This is why spinning objects keep spinning. It's because space has no preferred direction. If the laws of physics depended on which direction you faced, angular momentum would not be conserved. And time translation symmetry, the fact that the laws of physics are the same at all times, gives rise to the conservation of energy. This is why energy is conserved. It's because the laws of physics don't change over time. If the laws of physics were different yesterday than they are today, if the strength of gravity or the mass of an electron or the speed of light were changing over time, then energy would not be conserved. Let that sink in for a moment. Energy is conserved because time is symmetric. The reason you can't create energy from nothing or destroy it into nothing is that the fundamental laws governing the universe don't change from one moment to the next. The conservation of energy isn't just a rule, it's a consequence of the uniformity of time itself. This is breathtaking in its elegance. For nearly a century, scientists had known that energy was conserved. They'd measured it, tested it, relied on it, but they didn't know why. And now Noether showed them. The reason energy is conserved is the same reason that an experiment performed today gives the same results as one performed a century ago. It's because the universe is consistent. The laws of physics are timeless. They don't have a preferred moment. They work the same way now as they always have and always will. Think about what this means. If someone ever proved that energy could be created or destroyed, it would mean that the laws of physics were changing over time. It would mean that the universe at one moment was fundamentally different from the universe at another moment. It would mean that experiments performed today might give different results tomorrow. The entire edifice of science, which relies on the repeatability of experiments, would crumble. Energy conservation isn't just a law of physics. It's a guarantee that the universe is consistent and comprehensible. Now, let me be precise about something. Noether's theorem applies to closed systems, systems that aren't exchanging energy with their surroundings. In an open system where energy can flow in or out, the energy of that particular system can change. A pot of water on a stove gains thermal energy from the flame. A ball thrown upward loses kinetic energy as it rises, but in both cases, the total energy of the larger closed system is conserved. The pot gains energy, but the stove loses the same amount. The ball loses kinetic energy, but gains gravitational potential energy, and the total is unchanged. Conservation of energy doesn't mean that the energy of any particular object is constant. It means the total energy of everything, when you account for all forms and all objects, is constant. Let me connect Noether's insight to something that might be the most famous equation in all of physics. E equals mc squared. Einstein's equation, published as part of his special theory of relativity in 1905, revealed something shocking. Mass and energy are not separate things. They're different forms of the same thing. Mass is a form of energy, and energy has mass. The equation tells you the conversion factor. E is energy, m is mass, and c is the speed of light, about 300,000 kilometers per second. Because c squared is an enormous number, roughly 9 times 10 to the 16th in standard metric units. A tiny amount of mass corresponds to an enormous amount of energy. 1 kilogram of matter, if completely converted to energy, would release about 90 quadrillion joules. That's roughly the energy of a 21 megaton nuclear bomb, about 1,400 times more powerful than the bomb dropped on Hiroshima. This doesn't violate energy conservation. It extends it. Before Einstein, scientists thought mass was conserved separately from energy. You couldn't create or destroy mass, and you couldn't create or destroy energy. Einstein showed that what's actually conserved is the total of mass energy combined. Mass can be converted to energy, and energy can be converted to mass, but the total mass energy is always conserved. This is exactly what happens in nuclear reactions. In nuclear fission, a heavy atom like uranium splits into lighter fragments. If you weigh all the fragments, they weigh slightly less than the original uranium atom. The missing mass has been converted into kinetic energy of the fragments and radiation. In nuclear fusion, light atoms like hydrogen combine to form heavier atoms like helium. The helium atom weighs slightly less than the combined mass of the hydrogen atoms that formed it. Again, the missing mass has been converted into energy. This is how the sun works. As we explored earlier, the sun loses a tiny fraction of mass with every fusion reaction. What Einstein's equation reveals is why. That missing mass isn't gone. It has become the energy itself, about 3.8 times 10 to the 26th watts of power, radiating outward as light and other electromagnetic radiation, illuminating the solar system and warming the planets. The sun has enough hydrogen fuel to continue this process for another 5 billion years or so. Energy conservation with mass energy equivalence also explains why particle accelerators work the way they do. When protons collide at nearly the speed of light in the Large Hadron Collider at CERN, the kinetic energy of the collision can be converted into mass, creating new particles that didn't exist before. This isn't creating something from nothing. The energy for those new particles came from the kinetic energy of the colliding protons. Energy was converted to mass. The total mass energy before the collision equals the total mass energy after. The books balance. They always balance. In 1928, the physicist Paul Dirac used quantum mechanics and special relativity to derive an equation describing the electron. His equation predicted something unexpected. For every particle, there should exist an antiparticle with the same mass but opposite charge. The antiparticle of the electron would be a positively charged particle with the same mass, which Dirac called the anti-electron. This particle, now called the positron, was discovered experimentally in 1932 by Carl Anderson. When a particle meets its antiparticle, they annihilate each other completely. All of their mass is converted into energy, usually in the form of gamma-ray photons. An electron meeting a positron produces two gamma rays whose combined energy equals the total mass energy of the electron and positron. Conversely, if you have enough energy concentrated in a small enough space, you can create a particle-antiparticle pair from pure energy. This has been observed countless times in particle physics experiments. Energy becomes mass. Mass becomes energy. But the total is always conserved. Now let's talk about energy conservation in quantum mechanics, because this is where things get subtle and fascinating. Quantum mechanics, the theory governing the behavior of atoms and subatomic particles, is fundamentally different from classical physics. In the quantum world, particles don't have definite positions or momenta until they're measured. They exist in superpositions of multiple states simultaneously. Outcomes are probabilistic, not deterministic. The universe at its smallest scales is governed by probability and uncertainty. Does energy conservation hold in this strange quantum world? Yes. Absolutely yes. The total energy of a quantum system is conserved just as rigorously as in classical physics. Quantum mechanics is built on time translation symmetry just as firmly as classical mechanics is, so Noether's theorem guarantees that energy is conserved. But there's a subtlety. The Heisenberg uncertainty principle says that you can't simultaneously know the exact energy of a system and the exact time at which it has that energy with unlimited precision. There's a fundamental trade-off. The more precisely you know the energy, the less precisely you know the time, and vice versa. This leads to something that seems at first glance like a violation of energy conservation, though it isn't one. In quantum field theory, the most fundamental description of particle physics, empty space isn't really empty. It's seething with what are called quantum fluctuations or virtual particles. Pairs of particles and antiparticles can briefly pop into existence and then annihilate each other, all within the time allowed by the uncertainty principle. The shorter the time they exist, the more energy they can temporarily borrow. This is sometimes described as the vacuum borrowing energy for a brief moment. But here's the crucial point. These virtual particles don't violate energy conservation. They exist for such a short time that the uncertainty principle prevents any measurement from detecting the violation. If you actually measured the total energy before and after, you'd find it was conserved. The virtual particles are a bookkeeping device in our mathematical description of quantum field theory, not a literal creation of energy from nothing. The total energy of the quantum vacuum is constant. What's fluctuating is not the total energy, but the momentary distribution of that energy. The total ledger always balances. Some people claim that virtual particles prove energy can be created from nothing. This is a misunderstanding. Virtual particles are mathematical tools in our calculations, not directly observed entities. When physicists calculate the outcomes of particle interactions, virtual particles appear as intermediate steps in the math. They're incredibly useful for making predictions, and those predictions match experiments with extraordinary precision. But they don't represent actual violations of energy conservation. The theory that produces them, quantum field theory, is built on time translation symmetry, and therefore conserves energy exactly. Energy conservation has survived every revolution in physics. It survived the transition from Newtonian mechanics to Einsteinian relativity. It survived the transition from classical physics to quantum mechanics. It survived the development of quantum field theory, the standard model of particle physics, and every other advancement in our understanding of the fundamental laws. At every step, the principle has been refined, sometimes extended to include new forms of energy like mass energy equivalents, but never abandoned. The conservation of energy is arguably the most battle-tested principle in all of physics. It's been verified at energies spanning dozens of orders of magnitude, from the gentle warmth of a cup of tea to the violent collisions in particle accelerators, to the thermonuclear infernos at the hearts of stars. It's been verified at distances from subatomic scales to galactic scales. It's been verified in every branch of physics, from thermodynamics to electrodynamics to nuclear physics to quantum mechanics to cosmology. No exception has ever been found, and the reason it holds, the deepest reason we know, is Noether's theorem. Energy is conserved because the laws of physics don't change over time. As long as the universe remains consistent, as long as the laws that govern it today are the same laws that governed it yesterday and will govern it tomorrow, energy will be conserved. It's built into the fabric of reality, woven into the structure of time itself. But here's where the story takes a darker and more nuanced turn. Because while the total amount of energy in the universe never changes, something about that energy does change. Something irreversible, something that determines the fate of the universe and everything in it. The total energy stays the same, yes, but its quality degrades, its usefulness diminishes, and this process is unstoppable. Before we dive into that though, there's one more thing about energy conservation I want to explore. And it involves one of the most fascinating and nuanced areas in all of physics. The behavior of energy in general relativity, Einstein's theory of gravity. In 1915, 10 years after publishing Special Relativity, Einstein published his general theory of relativity. This theory describes gravity not as a force in the traditional sense, but as a curvature of space-time caused by mass and energy. Massive objects like stars and planets curve the fabric of space-time around them, and other objects move along the curves in that fabric. As the physicist John Wheeler famously summarized, matter tells space-time how to curve, and space-time tells matter how to move. In general relativity, the concept of energy conservation becomes more subtle than in any other area of physics. In a flat, static space-time, energy is unambiguously conserved. But the universe isn't flat and static, it's curved and expanding. And in an expanding universe, the simple statement that total energy is conserved becomes tricky to define. Here's the issue. When light travels across the expanding universe, it gets stretched, its wavelength increases. This is called cosmological redshift, and it's one of the primary pieces of evidence that the universe is expanding. A photon emitted by a distant galaxy with a certain energy arrives at Earth with less energy because its wavelength has been stretched by the expansion of space during its journey. Where did that energy go? This is a genuine puzzle. The photon had more energy when it was emitted than when it was received. The missing energy didn't go to any identifiable recipient. Space expanded. The photon's wavelength stretched, and its energy decreased. Period. Some physicists say this means energy isn't conserved in general relativity. Others argue that the energy was transferred to the gravitational field itself, to the curvature of space-time. Still, others point out that in an expanding universe, the concept of total energy simply becomes ill-defined. The truth is subtle. In general relativity, there's no single, universally agreed upon definition of total energy for the entire universe. Locally, in any small region of space-time, energy is perfectly conserved. If you zoom in on any small part of the universe, the equations of general relativity guarantee local energy conservation. But globally, for the universe as a whole, the concept becomes murky. This doesn't mean energy conservation is wrong. It means that in the extreme environment of an expanding universe with curved space-time, the concept of total energy needs to be handled with care. For all practical purposes, for every experiment we can perform, for every observation we can make of physical systems in our local region of space, energy is conserved with exquisite precision. The subtleties only arise when you try to define total energy for the entire expanding universe, which is a situation so exotic that it pushes the boundaries of our mathematical frameworks. Some physicists have argued that the total energy of the universe might actually be zero. This idea, sometimes called the zero energy universe hypothesis, suggests that the positive energy of all the matter and radiation in the universe is exactly balanced by the negative gravitational potential energy. If this is true, then the universe could have emerged from nothing without violating energy conservation. The total energy was zero before the Big Bang, and it's zero now. Nothing was created. The positive and negative energies just separated. Like a debt and a credit in an accounting ledger that perfectly balance. This is speculative, and not all physicists agree with it. But it's a fascinating possibility that shows how deep and subtle the concept of energy conservation really is. Even the origin of the universe might be consistent with energy conservation, if you account for all forms of energy, including gravitational potential energy. There's another area where energy conservation leads to fascinating insights: black holes. When matter falls into a black hole, it seems to disappear from the universe, but the energy doesn't vanish. The black hole's mass increases by exactly the amount of mass energy that fell in. A black hole is essentially a storage device for energy, locked away behind an event horizon from which nothing can escape. Or at least, nothing could escape, until Stephen Hawking showed in 1974 that black holes aren't perfectly black. Through a quantum mechanical process now called Hawking radiation, black holes slowly emit particles and lose mass. This is an incredibly slow process. A black hole with the mass of our sun would take about 10 to the 67th power years to evaporate. That's far longer than the current age of the universe. But in principle, given enough time, every black hole will eventually evaporate completely, releasing all its stored energy back into the universe as radiation. Energy is conserved even in the most extreme gravitational environments the universe can produce. Hawking radiation raises a famous puzzle known as the black hole information paradox. When matter falls into a black hole and the black hole later evaporates, is the detailed information about what fell in preserved in the Hawking radiation? Or is it lost forever? This question has been one of the most debated topics in theoretical physics for decades. But what's not debated is that the energy is conserved. The energy that went in comes back out. The total is preserved. It's the detailed information, the specific arrangement and identity of the matter that's in question, not the energy itself. Let me also mention something about how energy conservation plays out in everyday technology that most people never think about. Refrigerators don't destroy heat, they move it. A refrigerator takes thermal energy from the food inside and pumps it to the back of the unit, where you can feel it radiating warmth. The total energy in the room actually increases slightly when a refrigerator runs, because the electrical energy used to power the compressor is added on top of the heat removed from the food. Your refrigerator makes your kitchen warmer, not cooler. It just makes the inside of the fridge colder by moving heat from one place to another. Air conditioners work the same way. They don't eliminate heat, they pump it from inside your house to outside. If you left all your doors and windows open while running your air conditioner, the total temperature of your environment would increase because the air conditioner adds the electrical energy it consumes to the heat it's moving. Heat pumps, which are becoming increasingly popular for home heating, are remarkable illustrations of energy conservation. They don't generate heat, they move it. A heat pump extracts thermal energy from outside air, even in winter, and moves it inside. It uses electrical energy to drive this process, but the total heat delivered to your home is more than the electrical energy consumed. This isn't a violation of energy conservation. The extra heat comes from the outside air. The heat pump just moves energy from one place to another, using electricity as the power source for the transfer. For every joule of electricity consumed, a good heat pump can deliver 3 or 4 joules of heat to your home, because 2 or 3 of those joules came from the outside air, not from the electricity. This might seem like cheating, but it's perfectly consistent with energy conservation. You're not creating energy, you're moving it. The outside air gets slightly cooler, your house gets warmer, and the total energy of the system is unchanged. The electricity just provided the energy needed to drive the transfer process against the natural direction from cold to hot, which wouldn't happen spontaneously. And that brings us to a critical distinction, one that many people, even many science enthusiasts, fail to make. The total amount of energy in the universe never changes. But the usefulness of that energy, its ability to do work, its availability for driving processes that changes constantly. And it only changes in one direction, downward. This distinction is absolutely essential. When people hear that energy is conserved, they sometimes conclude that we'll never run out of energy. After all, if energy can't be destroyed, it's always there, right? We can just keep reusing it, right? Wrong. And understanding why it's wrong is perhaps the most important lesson in all of thermodynamics. It's the difference between having money and having money you can spend. Imagine you have $1,000, but it's been scattered as individual pennies across the entire surface of the earth. Technically, you still have $1,000. The total hasn't changed. But good luck buying anything with it. The money exists, but it's spread so thin that it's useless for any practical purpose. Energy behaves the same way. The total amount of energy in the universe is constant, but over time, energy tends to spread out. Concentrated energy becomes diffuse energy. Useful energy becomes useless energy. Hot things cool down, fast things slow down, organized energy becomes disorganized energy. And this process is irreversible. You can't put the toothpaste back in the tube. You can't unscramble an egg. You can't unshuffle a deck of cards back into perfect order by shuffling again. The total is the same, but the quality has changed. And it will never change back. Not on its own. This is the second law of thermodynamics. And it's where the story of energy takes its most profound and sobering turn. The second law of thermodynamics is often stated in many equivalent ways, but the most intuitive version goes something like this. In any natural process, the total entropy of a closed system either increases or stays the same. It never decreases. Entropy is a measure of disorder, of randomness, of how spread out and disorganized the energy in a system is. And the second law says that entropy always goes up, never down. Now, this might seem to contradict what I've been saying about energy conservation. If energy can't be destroyed, why do we talk about running out of energy? If the total energy of the universe is constant, why do scientists worry about an energy crisis? The answer lies in this: distinction between the total amount of energy, which is conserved, and the quality or usability of that energy, which is not conserved. Let me give you a concrete example to make this clear. Imagine you have a hot cup of coffee sitting on a table in a cool room. The coffee has thermal energy. It's at a higher temperature than the room. Because of this temperature difference, energy flows from the coffee to the room. The coffee cools down. The room warms up very slightly. Eventually, the coffee reaches room temperature. Equilibrium. Now, has any energy been destroyed? No. Not a single joule. The thermal energy that was in the coffee is now in the air in the room. The total energy of the system, coffee plus room, hasn't changed at all. Energy has been perfectly conserved. But something has changed. Something has been lost. Not energy, but the ability to use that energy to do something useful. When the coffee was hot and the room was cool, there was a temperature difference. That temperature difference could, in principle, be used to do work. You could use the heat flowing from hot to cold to drive a heat engine, to generate electricity, to power a machine. Not very efficiently with such a small temperature difference, but in principle, the temperature gradient represented usable energy. Once the coffee has cooled to room temperature, that temperature difference is gone. The same total energy exists in the system. But now it's evenly spread out. There's no temperature difference to exploit. No gradient to drive a process. The energy is still there, but it's useless. It's been degraded from a concentrated, useful form to a diffuse, useless form. This is what entropy increase looks like. The energy spreads out. The temperature differences disappear. The ability to do useful work diminishes. And here's the crucial point. This process is irreversible. The coffee will never spontaneously heat itself back up. The thermal energy that is spread through the room will never spontaneously concentrate itself back in the cup. You've never seen a cup of cold coffee sitting on a table suddenly start getting hotter all by itself while the room gets cooler. That would violate the second law of thermodynamics, and it simply doesn't happen. Note carefully what I'm saying here. The total energy is still conserved. The first law is not violated. But the distribution of that energy has changed in an irreversible way. The energy has spread from being concentrated in one place to being dispersed everywhere. And that spreading is a one-way process. Think of it like ink dropped into a glass of water. The moment you drop the ink, it starts spreading. It disperses. It mixes with the water. Eventually the ink is uniformly distributed throughout the glass, giving it a faint, even color. The ink molecules are still there. Nothing has been destroyed. But the ink will never spontaneously unmix itself, gathering back into a concentrated drop while leaving the water clear. The transition from concentrated to dispersed is natural and spontaneous. The reverse would require an input of energy and an organized effort. Left to itself, the system goes from ordered to disordered, from concentrated to dispersed, from low entropy to high entropy. The Austrian physicist Ludwig Boltzmann provided the deepest explanation for why entropy increases. In the 1870s and 1880s, Boltzmann showed that entropy is related to the number of microscopic arrangements, called microstates, that correspond to a given macroscopic state. A state where all the energy is concentrated in one place, like a hot cup of coffee in a cold room, has relatively few microstates. There are limited ways to arrange the molecules so that the coffee is hot and the room is cold. But a state where the energy is spread evenly has an enormous number of microstates. There are countless ways to arrange the molecules so that everything is at the same temperature. The second law then follows from simple statistics. If you randomly shuffle the arrangement of molecules, you're overwhelmingly likely to end up in a high entropy state, simply because there are so many more high entropy arrangements than low entropy ones. It's like shuffling a deck of cards. There's only one arrangement where the cards are in perfect order, ace through king of each suit, but there are approximately 8 times 10 to the 67th power different arrangements of a standard 52 card deck. If you shuffle randomly, the chance of ending up with a perfectly ordered deck is essentially zero. Not because there's a law against it, but because the ordered arrangement is just one possibility among an astronomically larger number of disordered arrangements. This is why entropy increases. It's not because there's some force pushing things toward disorder. It's because disorder is overwhelmingly more probable than order. The second law of thermodynamics isn't really a law in the same sense as the first law. It's a statement about probability. It's astronomically improbable, not theoretically impossible, for entropy to decrease in a closed system. But the numbers are so overwhelming that for all practical purposes, entropy increase is as certain as anything in physics. Boltzmann captured this insight in a famous equation carved on his tombstone in Vienna. S equals K log W. Entropy equals Boltzmann's constant times the natural logarithm of the number of microstates. This equation connects the macroscopic concept of entropy, something you can measure with thermometers and calorimeters, to the microscopic reality of atoms and molecules arranging themselves in countless different ways. It's one of the most profound equations in physics, bridging the world we see with the world of atoms. Now, let's think about what this means for the universe as a whole. The universe has a finite amount of energy. That energy is conserved. It will never increase or decrease, but the entropy of the universe is increasing. The energy is gradually spreading out, becoming more evenly distributed, less concentrated, less useful. Stars are converting concentrated nuclear energy into diffuse thermal radiation. Hot objects are cooling. Temperature differences are being erased. Gradients are flattening. This leads to a prediction about the ultimate fate of the universe that physicists call the heat death. In the far, far future, if the universe continues expanding and no new physics intervenes, all the stars will burn out, all the nuclear fuel will be exhausted, all the temperature differences will be erased. The universe will reach a state of maximum entropy, where the energy is spread as evenly as possible across all of space. There will be no temperature gradients to drive processes, no concentrated energy sources to power stars or planets or life. The universe will still contain exactly as much energy as it does today, not a single joule less, but the energy will be utterly, completely, irreversibly useless. The heat death is projected to occur on timescales that make the current age of the universe seem like the blink of an eye. Stars will continue forming for roughly 100 trillion years, about 7,000 times longer than the universe has existed so far. After that, the remaining stars will slowly burn out. White dwarfs will cool over quadrillions of years. Neutron stars will slowly spin down. Even protons, the building blocks of atoms, might eventually decay on timescales of 10 to the 40th power years, though this is still theoretical. Black holes will be the last bastions of concentrated energy, but even they will eventually evaporate through Hawking radiation. A stellar mass black hole takes about 10 to the 67th power years to evaporate. The largest supermassive black holes in the universe take about 10 to the 100th power years. That's a 1 followed by 100 zeros, an incomprehensible span of time, but eventually, even the largest black holes will be gone, their energy dispersed as Hawking radiation into the vast, cold, ever-expanding void. After the black holes are gone, the universe will consist of nothing but a thin, cooling soup of photons and subatomic particles spread almost uniformly across an unimaginably vast space. The temperature will be barely above absolute zero. There will be no structures, no stars, no planets, no galaxies, just a uniform, featureless expanse of almost nothing, slowly getting thinner and colder as space continues to expand. And yet, the total energy of the universe will be exactly what it was at the Big Bang. Every joule that existed at the beginning will still exist at the end. Nothing will have been created. Nothing will have been destroyed. But everything will have been transformed from concentrated, useful, ordered energy into diffuse, useless, disordered energy. The first law says the total doesn't change. The second law says that distribution does, and it only changes in one direction. Now, I mentioned earlier that dark energy adds a complication to this picture. Dark energy is the mysterious force that's causing the expansion of the universe to accelerate. We discovered this in 1998 when 2 teams of astronomers independently found that distant supernovae were dimmer than expected, indicating that the expansion of the universe is speeding up rather than slowing down. This was one of the most surprising discoveries in the history of cosmology and earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. Dark energy makes up about 68% of the total energy content of the universe. And as the universe expands and new space is created, the density of dark energy remains constant. This means the total amount of dark energy is increasing as the universe gets bigger. More space means more dark energy. This seems to violate energy conservation, and in a sense it does, at least in the way most people understand it. But here's the nuance. As I discussed earlier, in general relativity, the concept of total energy for the entire universe is not well defined in the same way it is for a system in a laboratory. The equations of general relativity guarantee local energy conservation. In any small region of space, energy is perfectly conserved. But globally, in an expanding universe with dark energy, the bookkeeping becomes complicated. The energy of dark energy increases, but the energy of other things, like photons losing energy through redshift, decreases. Whether these changes balance out depends on how you define total energy, and there's no universally agreed upon way to do that in general relativity. This is not a failure of physics, it's a reflection of how deep and subtle the concept of energy really is. In the controlled environment of a laboratory, energy conservation is absolute and unambiguous. In the exotic environment of an expanding universe with curved space-time and dark energy, the concept stretches to its limits. But even here, the local conservation of energy holds perfectly. In any experiment you could ever perform, in any physical process you could ever observe, the energy going in will always equal the energy coming out. The books will always balance. So where does all this leave us? What does the conservation of energy mean for our lives, for our place in the universe, for the human experience? Here's what I think is the most profound takeaway. You are made of energy that has existed since the beginning of the universe. The atoms in your body were forged in the cores of ancient stars. The energy that powers your thoughts was once nuclear energy in the sun, which was once gravitational energy in the collapsing gas cloud that formed the solar system, which was once the kinetic energy of matter flung outward in the Big Bang. Every breath you take, every heartbeat, every thought, every emotion, every moment of your existence is powered by energy that has been flowing through the universe for 13.8 billion years. And that energy will never disappear. When you die, the energy in your body will be transformed. It will become thermal energy, chemical energy, the energy of decay and decomposition. It will be absorbed by the soil, taken up by plants, radiated into the atmosphere. Eventually, every joule of energy that constituted you will be dispersed into the environment, recycled, transformed, passed along. The atoms that made up your body will join other molecules, become part of other systems, maybe other living things. The energy will continue its eternal journey from form to form, from place to place, never created, never destroyed. There's something both humbling and comforting in this. Humbling because it reminds us that we're not separate from the universe. We're made of it. We're temporary arrangements of energy and matter that briefly take the form of conscious beings before dispersing back into the cosmic flow. We're like waves on an ocean, briefly rising above the surface, having an experience, a perspective, a life, and then subsiding back into the water that was always there. But also comforting because it means nothing is truly lost. The energy that makes up you has been on a journey that spans the entire history of the cosmos. It existed before the Earth was formed, before the sun ignited, before the Milky Way took shape. It will continue to exist long after our star has died, and our planet has been swallowed or scattered. The universe is a vast, eternal recycling system, constantly transforming energy from one form to another, never losing a single joule. The conservation of energy tells us something deep about the nature of reality. It tells us that the universe is consistent. The laws of physics don't change from one moment to the next. Experiments performed today will give the same results tomorrow. The universe is comprehensible, rational, and lawful. And it's this very consistency, this time symmetry that Emmy Noether identified, that guarantees energy conservation. The The universe's reliability and our ability to understand it are not separate things. They're the same thing, seen from different angles, but the second law adds a melancholy note to this beautiful symphony. Yes, energy is eternal, but its quality degrades. The universe is slowly winding down like a clock that was wound up at the Big Bang and has been running ever since. The clock will never stop because the energy never disappears. But it's running slower and slower as the energy becomes more and more spread out, less and less concentrated, less and less able to power the complex processes that give rise to stars, planets, chemistry, biology, and consciousness. We exist in a special time, a time when the universe is still young enough to have concentrated energy sources like stars, a time when temperature differences still exist to drive weather and chemistry and life, a time when the entropy of the universe is still low enough that complex, ordered structures like galaxies, planets, and people can form and persist. This won't last forever. In the cosmic long run, entropy wins. The universe will reach thermal equilibrium, and the capacity for complexity will be gone. But that's trillions upon trillions of years in the future. For now, we live in a universe that's vibrantly alive with energy transformations. Stars are fusing hydrogen into helium. Planets are orbiting suns. Weather systems are churning across planetary surfaces. Volcanoes are erupting. Rivers are flowing. Plants are photosynthesizing. Animals are breathing, running, thinking. And you, right now, are converting chemical energy into the electrical impulses that allow you to comprehend these words. Let me make the distinction between the first and second laws crystal clear one more time, because it's so important and so often confused. The first law says the total amount of energy in the universe is constant. It never changes, not by a single joule. The second law says the distribution of that energy changes irreversibly over time. Energy flows from concentrated to dispersed, from hot to cold, from ordered to disordered. The total is the same, but the pattern changes. And the pattern only changes in one direction. It's like a sandcastle on a beach. The sand is all there. It never disappears. But wind and waves gradually erode the castle, spreading the grains across the beach. The sand isn't destroyed. It's redistributed. And while you can rebuild the sandcastle by gathering the sand and shaping it again, that requires effort. That requires energy input from outside the system. Left to itself, the castle only erodes. It never spontaneously rebuilds. Life itself is a beautiful example of how these two laws interact. Living organisms are highly ordered, low entropy structures in a universe that's constantly moving toward disorder. How is this possible? Doesn't the existence of complex life violate the second law? No. And this is a point that's frequently misunderstood. The second law says the total entropy of a closed system increases, but living organisms are not closed systems. They're open systems that constantly exchange energy and matter with their environment. A plant takes in sunlight and uses that low entropy, concentrated energy to build complex sugar molecules from simple carbon dioxide and water. In the process, the plant increases its own order, lowering its own entropy. But it also releases heat and produces other byproducts that increase the entropy of the environment by more than the plant decreased its own entropy. The total entropy of the plant plus its environment increases as the second law demands. You do the same thing. You eat food, which is concentrated chemical energy. Your body uses that energy to maintain its complex structure, to repair cells, to think, to move. But your body also radiates heat, produces waste and increases the entropy of your surroundings. The total entropy of you plus your environment is always increasing. You're not violating the second law. You're exploiting a loophole. You're using the flow of energy from concentrated to disperse to do useful work along the way. Life surfs on the wave of entropy increase, extracting useful work from the flow of energy from order to disorder. Earth as a whole does this too. The sun provides a concentrated, low-entropy source of energy, short-wave radiation at about 5,800 degrees. Earth absorbs this energy and re-radiates it as long-wave infrared radiation at about 255 degrees. The total energy absorbed equals the total energy radiated. Energy is conserved, but the outgoing radiation has much higher entropy than the incoming radiation because it's at a lower temperature and therefore more spread out. The difference in entropy between the incoming and outgoing radiation is what drives all of Earth's weather, its oceans, its geology, and its biology. Life on Earth is powered by the entropy difference between sunlight and infrared radiation. This is why the heat death of the universe would be the end of all complexity, all life, all possibility of interesting things happening. It's not because the energy would be gone. The energy would all still be there. Every last joule, but with no temperature differences, no gradients, no concentrated energy sources. There's nothing to drive processes, nothing to power complexity, nothing to sustain life. The universe would have all its energy and none of its potential. There's one more thing I want to address about energy conservation before we close, because it comes up frequently and deserves a careful answer. People sometimes ask, if energy is conserved, where did the energy of the universe come from in the first place? If energy can't be created, how did it get here? This is one of the deepest questions in all of science, and we don't have a definitive answer. But there are some fascinating possibilities. Remember the zero energy universe hypothesis I mentioned earlier? If the total energy of the universe really is zero, then the Big Bang didn't create energy at all. It separated zero into positive and negative components, like writing zero as +1 plus -1. No energy was created because the total remains zero. The universe is, in a sense, nothing elaborately rearranged. Other physicists point out that the question, where did the energy come from, might not have a meaningful answer. The laws of physics, including energy conservation, describe how the universe behaves, not how it was created. Asking where the energy came from might be like asking what's north of the North Pole. The question assumes a framework that doesn't apply. The laws of physics, as we understand them, might only apply within the universe, not to the origin of the universe itself. These are open questions at the frontier of physics and philosophy. We don't know the answers yet, and we might not ever know them. But what we do know is that within the universe, from the first fraction of a second after the Big Bang to the present day and on into the far future, energy is conserved. Whatever total the universe started with, that's the total it will always have. The conservation of energy is not just a physics equation, it's a story about how the universe works, about where we came from, and about where we're going. It tells us that nothing is ever truly lost, that every sunset is a transformation, not an ending, that every death is a redistribution, not a disappearance, that the energy powering your awareness right now has been on an unbroken journey since the very first moment of existence. When you look at a candle flame, you're watching ancient solar energy being released. The wax was made by bees from nectar, which was made by flowers from sunlight, which came from nuclear fusion in the sun, which came from gravitational collapse of a hydrogen cloud, which came from the Big Bang. The flame is a tiny link in a chain that stretches back to the beginning of time. And when the candle burns out, the energy doesn't disappear. It merely continues its journey in a new form, warming the air, radiating into the room, eventually into space, joining the Great Dispersal, the slow increase in entropy that will continue for as long as the universe exists. So the next time someone asks you where energy goes, you can tell them. It doesn't go anywhere. It transforms. It changes shape, changes form, changes location, but it never, ever disappears. It can't. The symmetry of time itself forbids it. As long as the laws of physics remain the same from one moment to the next, as long as the universe stays consistent and comprehensible, energy will be conserved. This is one of the deepest truths we've ever discovered about the nature of reality. And you, sitting here right now, are living proof. You're a temporary arrangement of ancient energy, a pattern in the eternal flow, a brief and beautiful configuration of atoms and forces and fields that has existed in one form or another since the universe began. The energy that is you has been starlight. It has been hydrogen gas drifting through interstellar space. It has been nuclear fire in the heart of a star. It has been the light that crossed 93 million miles of void to reach a green leaf on a blue planet. It has been glucose in a plant cell. It has been food on your plate. And now, for this brief moment, it is you. Conscious, aware, wondering about the universe. That energy will continue long after you're gone. It will take new forms, join new systems, power new processes, and somewhere in some distant future, the same energy that once animated your thoughts might warm another world or power another mind or shine as part of another star. Nothing is lost, nothing is created, everything is transformed. That is what it means for energy to be conserved. Not just a law of physics, but a promise. A promise that the universe keeps its books. A promise that nothing real ever truly disappears. A promise written into the fabric of time itself, guaranteed by the deepest symmetry we know. Thank you for joining me on this journey through one of the most fundamental ideas in all of science. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the universe and the laws that govern it. And remember, the next time you feel your coffee growing cold, you're not losing energy. You're watching the universe do what it's always done, transforming, redistributing, and conserving every last joule. The energy in that cup has been on a 13.8 billion year journey, and it's not done yet. It will never be done. Good night, and may you never think about energy the same way again.